We've talked about a lot of topics in this news segment about basically expanding our economy and civilization into space. And what does it take to do that? And we've talked about all these topics I'm listing here, and we'll continue to talk about them because there's always progress made on them. Things like mining on the moon, on asteroids and other planets, also called in situ resource utilization. If you're going to go off and live off the planet somewhere, you can't just keep bringing stuff from Earth. It's just too expensive. You need to start figuring out how to live off the land. And that means, at a minimum, getting water, probably getting some metals, maybe some hydrocarbons, and also at a minimum, just getting material to build your habitats. You know, instead of bringing a giant steel structure with portholes and stuff to look out of, you're probably going to be covering it with regolith, the dirt from, let's say you're on the moon. You need it for radiation shielding, for instance. And when they figure out how to use it for agriculture, it'll take some chemical treatment, but at some point they'll figure out how to do that. Then there's manufacturing in space, and we've talked about a lot of those kind of things before too. You can manufacture things that you deliver back to Earth, and some of that's been done with pharmaceuticals in particular, and also crystals for a variety of uses, but also on the moon or from asteroids. You can make oxygen and make rocket propellant. Things like that. If you're going to expand into space, you have to be able to start doing it from space because it's a lot cheaper to ship it from an asteroid or from the moon than it is to ship it from Earth because the gravity is just so much more. Agriculture, forestry, space-based solar power is another one. You need to get a lot of power, and you're going to be using solar cells to do that, as well as nuclear reactors. And also taking a step back, part of this whole process is simply even just satellites. You know, we talk a lot about different kinds of satellites, and it's not because people are in them, but it's because you're in fact building an industrial capability to support activity in space. And it didn't matter what there are. They could be spy satellites. They could be used for monitoring agriculture. They could be monitoring the climate, you know, and all these things are being done. But the fact is more and more of that is being done, and we're getting more dependent on that. But in the process of doing that, we're improving the reliability of rockets. Hardware costs are coming down drastically. And we're building experience on how to operate in space, even when people aren't there, just even making sure the machinery works. Because the machinery doesn't work, the people certainly can't live there because they depend on the machines. So all that is really kind of reaching a takeoff point. I've actually taken some pictures from some of our previous discussions, like mining of an asteroid. We're sending the Psyche mission to go and do some prospecting there. It's a huge metallic asteroid. Space-based solar power, solar cells being on the moon, being built on the moon. Blue Origin says they can do it. They've actually worked out the technology. In general, having structures, solar cells, having a little bit of agriculture, all that kind of stuff. And that was actually a particular company's manufacturing process where they were making pharmaceuticals or crystals in space and then bringing them back to Earth and figuring out how to do that cheaply. So all that's happening. But there's a new one, kind of a new kid on the block that I have to admit I hadn't thought of until recently either. And then all of a sudden it's made some news. Data centers in space. And immediately you're going to think, what? You know, why would you do that? Well, actually, there's a lot of power needs from them, and they are growing very, very rapidly. They're taking more and more power. Now, the European Union, in one of their studies, estimated that there's probably going to be about 23 gigawatts of power consumed by 2030. I think a lot of other people think it's a lot more than that. And a way to look at this is, what is this? Well, that says you're going to collect solar energy up in orbit, and instead of sending it back to the ground, which is the thing in space-based solar power, and which is the hardest step in that, why not just consume the power? You know, what gets generated in space stays in space. All you have to send back is the information. You don't have to send the power. In my mind, this actually could be the first practical large-scale solar use that could happen in space, because we already know how to do all this stuff. It's just a matter of scaling up. Whereas transmitting the power back, that's a much harder problem. You got to convert it to microwaves, send it down, have square miles of antennas on the ground, which we probably won't even be able to get permits for because people are afraid of it. You know, that's all just going to take forever. This actually could be a much more rapid way of getting things going. In terms of why do data centers come in? The biggest single driver right now is training AI. Now, in my mind, actually, there's what's called the hype cycle put up by the Gartner Group, where, you know, people get really, really excited about technology, and then they have these wild initial enthusiasms, and a lot of money gets spent, and most of it is wasted. And then people get realistic, and then the enthusiasm goes down. But then over time, drops off, but eventually then it kind of goes back, and eventually will come back up much further in the future. Most technology goes through this hype cycle, and I think right now we're already past the peak on that one. where people are saying, wait a minute, this stuff, it just doesn't really work that well. And nor can it. But it doesn't matter. Right now, it is a big driver for data centers. I'll give you an example, not even counting the AI training, Amazon Web Services. They just bought a data center from a power company in Pennsylvania. Actually, it's Talon Energy, which is a Houston-based company. There's a 2.5 gigawatt nuclear plant in Pennsylvania. That's actually, that might be the biggest one in the US. There's a building, I've seen the aerial picture, right next to it, there's this big data center, and it had been started by that energy company. Amazon's going to build that out, but they're going to take a gigawatt.
Where's that located?
Susquehanna is some little town near Susquehanna, Pennsylvania.
Okay.
It's pretty rural. I see the aerial pictures, there's just woods all around it. Big power lines, heading out from it. A typical nuclear power plant in the US is more like a gigawatt. This is actually an unusually large one for the US. The largest ones are maybe 5 gigawatts, and largest is actually 8. But those all exist in other countries. But anyway, this is a big one. But the point is they're going to consume a significant portion of that entire nuclear power plant output. And this is not unusual. People like Meta and all these other companies, they're all frantically looking for sources of power. And of course, they all want to have green power, and at least there's no carbon dioxide generated by the nuclear plants, so they're especially favored. They pretty much used up all the hydropower and all that kind of stuff. There's some town in Texas where people are complaining about that they're using it for crypto mining. They essentially have their own power plant. There's a lot of this going on, you just don't realize. But cloud services in general are generating a lot of need for this. Now, I think there's probably other examples that are better compared to AI training. The problem with AI training is that you need a lot of information. Basically, a lot of data has to go up. There's the training data. That's a huge amount, and that's going to be a bottleneck. So I think that's actually not going to be the best model. The best model will be things that take a lot of computing time, but don't require a whole lot of data. Well, cryptocurrency mining, that's the big one. And that's also been consuming vast quantities of energy. And also just large-scale simulations, people doing weather or climate studies, or even engineering design. There's huge amounts of power going into that right now. And actually, a lot of that could be handled up there. And there's also examples of data that starts in space. All the satellite, for instance, all these satellites that are observing Earth, they're like taking pictures or radar pictures. What do they do with it? Well, there's way too much of that for a person sitting in an office to look at. They have to have software that scans over it, looks for patterns like changes, say, okay, we see now that there's 3 Russian tanks here instead of 1, and that kind of thing. Or we see that there's a whole lot more ships suddenly diverting from their normal paths because they're avoiding being shot at by the Houthis or something. That kind of stuff is going on all the time, but it takes a lot of analysis, and that's being done by software. And that can just as easily be done there. And again, you don't even have to send back as much information. You don't need to send the entire pictures. You can send the analysis for the 5% of them that actually are important. So anyway, those are all good examples of things that could be done in space.
That's the CIA analysis in space.
Yeah, but it's also every other kind of thing too. I mean, there's an awful lot of climate monitoring kind of stuff. There's just an awful lot that goes on. The weather alone, I mean, that's a huge thing. And that takes immense amounts of power. When they do all those calculations on hurricane paths and stuff, that's an immense amount of computing. So the arguments are, well, there's really no pollution. I mean, again, what is generated in space stays in space. There's no pollution, there's no greenhouse gases, and there's no cooling water users. That's actually pretty significant in some places. You got a big cooling towers, there's a lot of evaporation off of cooling towers. If you're in the middle of a desert somewhere, you don't have a lot of that, so, that doesn't work so well. So what do you compare it to? Well, you compare it to terrestrial solar power. Turns out it's much more efficient to do it up in space for a variety of reasons. The biggest single one is just the day-night cycle. You're not generating power at night. You go up in a high enough orbit, or one I'll talk about in a minute, you go up in a high enough orbit and you can operate 24 hours a day or close to it. That's a 50% factor right there. Seasons, weather, and just the atmosphere itself attenuates, it gets absorbed by the air. So that's calculated by a capacity factor where you say, okay, there's a nameplate capacity, which is what you can get, peak day time, noon kind of numbers. You actually end up with about 24% compared to the nameplate capacity in the US. Actually, Northern Europe only gets about 10%. There's a company I'm going to talk about. They say on average, it's about 5 times more efficient to get your power generated in space than it is by doing the same solar power down on Earth.
A solar array to generate a gigawatt.
Yes, I'll get to that. Oh, we're talking square miles, but you have it in space. So part 2, now the next comparison is, well, what about space-based solar power? A big array of solar cells up in space, you convert them to microwaves, You send them down to a giant antenna where literally square miles, 7, 8 square miles are the typical kind of things. It's called a rectenna. It's an antenna plus rectifier where you generate DC. And then from there, you have to convert that to alternating current to then feed back into the grid. There's a lot of inefficiencies along the way, and it's a lot of land, a lot of permitting, and all that kind of stuff. It's basically, that is the hard step right now. The technology hasn't really even been proven for any significant distance. You can do it for a mile or something, but it hasn't really been demonstrated on any scale yet. So there's a lot of uncertainties with the technology. The good part about this is space-based solar power, but not transmitting it down, which is the hard step. You're not really constrained by physical limits, not really, not like you are on Earth. And it's easier to control because the environment's a lot more stable too. You can do temperature control a lot better. Now, the European Union has taken an interest in this. They have a project called Ascend. It's an incredibly long acronym. And so they put up some money to do feasibility studies. Now, I think their goals are extremely timid. Like, they're hoping that by 2036, they can get an operational system, and by 2050, they could do a gigawatt of capacity. This is not anywhere near enough. They've already issued their first report, which basically said, this looks good, let's do more study. It's just like a classic academic study, right? That's the last sentence in every academic study is, further research is needed. But it's true. I think that there's something to it. Now, what's interesting about them, though, is their emphasis is really on the environment. That is, it's part of what they call the Green Deal. So what they're saying is it doesn't really have to be economically viable. It just needs to get rid of a lot of pollution or greenhouse gas generation on Earth. And also, there's a subtext. It actually said it, though. I was reading some of their documents. They've fallen way behind in the rocket business, the launch business. They don't even have a reusable rocket yet. And there's a lot of thought that they shouldn't even bother. Basically, they're just going to go with what they have, which will always be more expensive, but at least they'll have their trained core of engineers and scientists that know how to build rockets. So they got two major incentives that actually don't even involve economics. There are companies involved in this. It's led by a group called Thales Linea Space, which is a Spanish version of Thales. A lot of people here might not have heard of that. Actually, they built a lot of stuff that we put, like the Bishop Airlock. They're the ones that actually do all that heavy-duty metal work to build these big vessels. The Bishop Airlock, the Axiom space station. There's a couple of Houston companies right here that are actually getting a lot of the work done, and that was by the Italian subsidiary. But anyway, Ariane Group, which launched, they were the ones that sold the rocket launchings, Airbus, and so on. Hewlett-Packard Enterprise. Oh, where's Sonia's gone? That's too bad. She'd be thrilled to know that somehow they're part of the European Union. Okay, anyway, there's interest by private companies here, which I think will actually be far more important. There's a startup that just got going at the very end of last year, beginning of this year. They have a plan to put up 300 satellites to process data in space, and they're going to launch a demo in May 2025. And they say they have a paying customer for this already, and maybe several others that might do something. And they actually hope that by the following year, they could create at least a portion of the network. Now, what's interesting is they put out a white paper this month, and that's actually what drove this presentation. That is much more visionary. What their business plan is a bunch of little satellites in very, very low orbit. What they're now saying in this white paper is have the gigantic station, and that's a 4 kilometer by 4 kilometer array of solar cells there, which is the same kind of thing you need for space-based solar power, but they're just saying, in the center of that, just put your computer.
By the way, 4 kilometers by 4 kilometers is 2.4 miles by 2.4 miles.
Their goal is to have a 5 gigawatt data center, which is like a very large nuclear power plant. And that's the one that would have the 4 kilometer by 4 kilometer solar array. Now, what's interesting is how they're going to do that. And what they're doing is they're saying, okay, half of the Earth is always illuminated by the sun. You want to be there. Now, one way to do that is to be far enough away from the Earth that you're never in the shadow of the Earth. You're never covered up. But the other way to do it is to be in an orbit perpendicular to that, so that the sun comes in, and no matter where you are, or at least if you're close to that orbit, you're going to go ahead and get power. And that's actually possible to do with what's called a sun-synchronous orbit, and that's what they're proposing. Here's a picture to explain this. Your eyes may glaze over at this, but it's actually not as messy as it looks. Here you're looking down. Imagine that the Earth is going around the sun there. The blue thing is the Earth. It forms a plane, and that's this flat screen right here. And it's going counterclockwise. That's what that little arrow over there means. And they're just showing you the yearly path of the Earth. So there's 4 different times where they're taking a snapshot. Now, you can have an orbit, this green one here, It's not actually exactly perpendicular, but if it's close to that, most of the time you'll be exposed to the sun.
On the side of the solar array facing the sun. But by the time the Earth moves ahead 3 months on that diagram, that green orbit around the Earth also has to rotate to a different position. Earth orbits the sun once per year, so that green orbit around the Earth has to rotate around the Earth once a year also.
And if you do that, that's called a sun-synchronous orbit. And they can do it hovering right on the boundary between day and night. And that's up at like 800 kilometers, just below the radiation belt. There is a video of this, just to give you a sense of the scale. So there's the data center there in the middle of this giant thing. That was it. That's just basically their very short ad. For all the space-based solar power stuff, you need really big arrays. One way or another, you need a lot of solar cells. And it just seems like, well, this might be a reasonable way to get started with it. Now, a question came up before about Amazon's Project Kuiper, which was their network of satellites. Probably they're going to get involved in this one way or another, either Amazon directly or in Blue Origin. And they are, to some extent, already involved because Axiom Space, they're the ones that are building an attachment to the space station, the existing space station. And then eventually, when the space station goes away, they'll still be there. They are going to put a data center in there. And they're integrating that with Amazon Web Service. So Amazon is involved already to some extent. That's going up in 2026, 2027. It's already going to happen. It doesn't take any big R&D effort. They're just going to do it. And what they'll probably do is just tie in with their network if Amazon gets it built fast enough, which is still not very clear. They could always go through Starlink if they had to. Other entries are in there too. Japan has a couple companies. All right, so challenges with this. Maintenance. How the heck do you maintain the thing? Well, when pieces fail, you just have to be able to move them out and drop them back in the atmosphere or bring them back. So that means a very modular architecture, and they'll have to have robotics to do this. You're never going to be able to have a bunch of astronauts up there maintaining this stuff at any reasonable cost. The environmental issues are probably the biggest one. I mean, you're going to generate some orbital debris just from the launches. There could be collisions and all that. Vulnerability to attack, I think that's actually going to be the biggest single problem, is putting a lot of money into something that's very easily destroyed. And you're at risk. The way the world is heading, we probably are going to have limited warfare in space, and something like this would be a big
target. Another possible issue.
I don't know if this is really a serious issue, but there's a heck of a lot of radiation, infrared, that has to get dumped by the radiators on this thing. And how much? Well, exactly the amount that's generated in power. You got all this power being generated by the solar cells. Essentially, all of that has to be radiated off. It's just an energy balance. Otherwise, it'll keep getting hotter and hotter. So that's a lot to dissipate. Now, they're going to radiate it. A lot of it might be directed in some direction. And if you're really close to that, that could be a problem. Cost, of course, is still the big question. That 5 gigawatt unit, the computing plus the solar power cells, might take 200 Starship launches. So you're not talking small scale. This only is practical when you have much, much cheaper access to space. And that's what Starship is promising. But of course, it isn't there yet. So all of this is really depending on that. The radiator area, which is what's going to reject all this heat into space, that's about half the size of a solar array. So you got this big area of solar cells. You've also got to have a lot of radiator. That's a lot of cost. Shielding for the electronics, because you're up, you're getting pretty close to the radiation belt there. And also the chips, which are actually the thing that are hot in the computers, you got to get that heat transferred ultimately out to those radiators. How they're going to do that, not clear. You're not going to use cooling water. It's too cold up there for that. So how they're going to do it is not clear. And maybe transmission delays.
Questions arose about the radiation in space impacting computers, testing and scaling up the size gradually.
I think they're just going to have to get experience with that. But we have a lot of experience with computing in space. Even on the space station, there have been small data centers put in. Actually, Microsoft did one a couple of years ago, just with servers. And people up there with laptop computers and everything. So at the level of the space station, it's apparently not that bad. And if they're going up a little bit higher than that, then that's more of an issue. But that's right. You're never going to build the whole thing all at once. You're going to build small scale in modules. You're going to have some solar cells and some computing. If that works, then you're going to expand it. There has to be a modular approach. It can't be all or nothing. That's it.
Other space-related videos or slide presentations by me are available at the link shown here. That includes a list of videos at my YouTube channel, so you can view them or subscribe for notifications about future videos. These presentations are mostly made as part of the meetings of National Space Society's North Houston chapter, and the link to that is shown. Topics like these are presented as part of a monthly news segment, and there are also lots of other interesting speakers and open discussions. You can attend in person or online via Zoom. Come join us.